you've ever walked across a city on a hot summer afternoon, you know how much a difference a single tree can make. Step out from an open sidewalk and into the shade, and the temperature seems to change almost instantly. And in cities where concrete and asphalt trap heat, trees can be one of the simplest tools for making a neighborhood more livable. But trees are doing more than casting shade. They're also releasing chemicals into the air. And when some of those compounds mix with pollution and strong sunlight and heat, the chemistry can change, sometimes making summer air unhealthy to breathe. New research is showing that when it comes to urban forests, the type of tree we plant may matter more than we once realized. Welcome back to the podcast. I'm Dr. Mack, and this is the Climate Translation. When we look at a tree, most of us think about what it takes out of the atmosphere, namely carbon dioxide. Many of us learned about photosynthesis in school. Plants take in carbon dioxide, use sunlight to build sugars, and then release oxygen back into the air. But the exchange can go in different directions. Trees are constantly releasing other substances into the atmosphere as well. Water vapor is one of them. Trees pull water from the soil, move it through their roots and trunks, and eventually release it through tiny openings in their leaves. But they also release hundreds of different organic chemicals. Scientists call many of these biogenic volatile organic compounds, or BVOCs. The name sounds intimidating, but you can break it down pretty easily. Biogenic means it came from a living thing. Organic tells us that the molecule contains carbon, and the volatile means that the substance can easily evaporate and enter the air. You've probably experienced some of these compounds without even realizing it. Think about that unique smell of a pine tree, or the scent that's released when you crush a leaf between your fingers. Those smells come from volatile chemicals produced by the plant. One of the most important BVOCs for our story is isoprene. You probably won't smell it when you're walking beneath a tree, but plants around the world release enormous amounts of it into the atmosphere every year. Isoprene appears to help plants deal with environmental stress, particularly heat. The leaf, sitting in a direct summer sun, can become increasingly warmer than the air around it. At high temperatures, the structures inside the plant cells that carry out photosynthesis can become stressed. Research has shown that plants capable of producing isoprene are better protected against short periods of intense heat. In a sense, it's part of the plant's defense system. And while a lot of plants produce that chemical, not every tree produces the same amount. Some species release very little isoprene. Others release a lot. Oaks are well-known isoprene emitters. So are poplars, willows, and eucalyptus trees. Other species produce different compounds, including chemicals called monoterpenes. So while all of these trees have the potential to provide us shade from the sun, chemically they behave very differently from one another. And that difference is at the center of new research that was just published in August of 2026. A team led by Xian Junhe and Ben Yuan at Jinan University in China, working with researchers including an atmospheric scientist, Thomas Karl, at the University of Innsbruck in Austria, studied emissions in Beijing. It's a city that offered them an interesting natural laboratory. The capital of China has millions of trees, including large numbers of willows and poplars. The researchers wanted to understand exactly what those trees were putting into the atmosphere. But what they discovered wasn't simply that the trees were releasing chemicals. They also found out how important those chemicals could become once they entered the air above a hot, polluted city. You've probably heard of ozone. It's a chemical in the stratosphere, far above our heads, that absorbs and protects us from the harmful UV radiation from the sun. But ozone can also be found at the surface. In fact, it's one of the primary components of what we call smog. It all starts with nitrogen oxide, sometimes called NOx. It comes mostly from human activity. It's a byproduct of combustion engines as well as power plants and industrial facilities, and can occur wherever fuel burns at high temperatures. In a large city, there can be a lot of NOx in the air. And then you have to consider volatile organic compounds. Some are released by trees, but others come from gasoline, paints, solvents, factories, and countless other human sources. Then you add in the final ingredient, sunlight, and chemistry begins. Strong sunlight provides energy that breaks apart and rearranges molecules in the atmosphere. When nitrogen oxides and volatile organic compounds are present together, they can enter into a complicated series of reactions. The exact chemical processes are not necessary to understand the result. But think of it as a recipe being followed. First, you've got oxygen in the atmosphere. Then you add in NOx as the next group of ingredients. Volatile organic compounds are added, and then sunlight supplies the energy needed to start mixing everything together. One of the products that can emerge from that chemistry is ozone. And while ozone high in the air is beneficial, ozone at the ground is not. It's the same molecule, 3 oxygen atoms joined together. But in the lower atmosphere, where we live and breathe, ozone is a pollutant. It can irritate your lungs, it can make breathing more difficult, and it can worsen conditions like asthma. And unlike smoke coming from a wildfire or exhaust coming from a tailpipe, ozone isn't released directly from a source. There isn't an ozone pipe sticking out the back of your car. Instead, ozone is forming through those chemical reactions in the atmosphere after other pollutants have already been released. Meteorologists and air quality scientists thus call it a secondary pollutant, and it's one reason ozone can be difficult to understand. You can walk outside on a perfectly clear summer afternoon. You don't see smoke, and there may not be any obvious haze or smell, but the chemistry above your head is very active. And the weather matters too. Ozone tends to be a problem on hot summer days because sunlight drives the reactions that produce it. If winds are light, pollutants can also remain over the same area for longer periods of time, giving time for those chemical reactions to occur. This is why many cities issue ozone alerts during stretches of hot summer weather. I remember announcing many ozone action days during my time as a TV meteorologist in Corpus Christi, Texas. So that brings us back to the trees in this picture. A tree releasing isoprene is providing one of the ingredients that can take part in that chemistry. It's a reactive chemical that can become part of the soup that makes up smog. And researchers wanted to know how much this chemical could influence ozone chemistry when trees are planted inside an atmosphere that already contains all the other ingredients needed to make it. And what they found is that rising temperatures due to climate change may impact this influence far more than they initially thought. In the study in China, the researchers wanted to move beyond simply estimating what trees might be releasing into the atmosphere. They wanted to measure it directly. So they installed instruments on Beijing's meteorological tower, including equipment on a platform about 330 feet above the ground. From there, they could measure the movement of volatile organic compounds from the surface and the atmosphere above it. And when they analyzed the results, they found something that looked strange. The compounds coming from vegetation were only about 1/10 of the total volatile emissions they measured. Most of the volatiles were associated with human activities. But the researchers weren't interested about how much chemical was present. They wanted to know about chemical reactivity. In simple terms, reactivity tells us how quickly a chemical is likely to participate in the reactions taking place in the atmosphere. A high reactivity means it's much more likely to produce a product. A low reactivity is the opposite. And by that measure, the trees suddenly became more important. Now they found that those volatile biogenic compounds accounted for nearly half of the total chemical reactivity that was observed, and most of that came from isoprene. In fact, isoprene alone accounted for more than 90% of the reactivity from plant-based volatiles. But the part of the study that really caught my attention was what was happening as temperatures have increased. When temperatures rose from 68 degrees Fahrenheit to 95 degrees, the chemical reactivity of those volatile compounds that came from vegetation increased by 7 to 8 times. The reactivity of volatiles from human activities increased by only about 40%. So as the day became hotter, the balance shifted. At cooler temperatures, vegetation only accounted for about 21% of the total reactivity going on. At hotter temperatures, that climbed to 74%. The chemistry had changed because the trees were responding to the heat. And on days when ozone production was especially sensitive to the amount of volatiles in the air, the researchers found that the peak ozone concentration increased with temperature at nearly the same rate as that volatile reactivity. In other words, as it became hotter, plants were producing more reactive chemicals and releasing that into an air that already contained the ingredients needed for smog. The researchers then compared Beijing with more than 20 other cities, and Beijing stood out. It wasn't simply because the city had a lot of trees, it was because of what trees were growing there. About 35% of Beijing's urban trees are species known to release isoprene, including large numbers of weeping willows and Chinese white poplars. Across the cities the researchers examined, isoprene emissions varied by more than tenfold, depending largely on the mix of tree species. And that might be the most important finding of this study. As cities are getting hotter due to man-made climate change, the question is no longer simply how many trees we plant, it's the types of trees we choose. So after hearing all this, you might reasonably ask, should we stop planting trees in cities? And of course the answer is absolutely not. And the researchers behind this Beijing study were very clear on that. Thomas Karl from the University of Innsbruck, he emphasized that their findings are not an argument for removing mature trees or reducing urban green space. Trees provide too many benefits. They shade our streets and our buildings. They cool the air through evaporation. They capture airborne particles. They absorb carbon dioxide, and their roots help slow stormwater runoff. And beyond the atmospheric science, trees simply make cities more comfortable and beautiful places to live. The lesson from the research is not that we need fewer trees, it's that we need to become more thoughtful about what trees we plant. For decades, urban forestry decisions have focused on practical questions. Will the tree survive the local climate? How much water does it need? Will the root damage the sidewalks? How large will it grow? Is it resistant to insects and disease? These researchers are suggesting that cities ask another question. What does this tree release into the atmosphere? That doesn't mean there's one perfect species that every city should plant either. The answer will be different depending on the climate, the local vegetation, and the pollution that's already present in the air. A tree that may work well in Helsinki may not be the best choice for Beijing. A species planted in Atlanta may behave different than one growing in Phoenix. This is urban planning becoming a lot more like atmospheric science. You have to consider the whole system. The researchers demonstrated what that can mean in Beijing. They estimated that if the city gradually replaced about 1/10 of its trees with the highest isoprene emissions with lower emitting species during normal tree replacement, the total isoprene emissions could fall by almost 30%. Thus, they suggested that as trees died, became damaged, or had to be replaced, the type of tree that took its place should be carefully considered. In effect, they suggested that cities use atmospheric chemistry as one more factor in deciding what gets planted next. And there's another thing to consider. Remember the recipe we discussed earlier. Isoprene by itself does not create ozone. You need nitrogen oxides, which are actually a larger component of the soup of smog. And much of that NOx comes from human activity, such as cars, trucks, power plants, and industry. That means reducing NOx emissions remains one of the most important ways cities can control ground-level ozone and smog. Tree selection would complement these efforts, not replace them. And this becomes especially important as cities warm due to climate change. Hotter weather can increase emissions from vegetation at the same time that strong sunlight is driving that ozone chemistry. So the urban forest of the future may need to do several jobs at once. Yes, provide shade, handle heat, survive drought, and support wildlife, but also interact with the atmosphere in ways that don't add to an existing pollution problem. If you can tell, the message is more complicated than saying plant more trees. Trees are important. We need to continue to increase their canopy, especially in highly dense urban environments. But just as important is the type of tree we select. The question is not whether cities should become greener. The question is how we design greener cities that also have cleaner air. When we step beneath a tree on a hot summer afternoon, we note their benefits. But this research reminds us that the tree is also part of the chemistry of the air around it. And that chemistry depends on the species, the temperature, the sunlight, and the pollution already present in the city. Planting more trees can make our cities cooler and more livable, but choosing the right trees while continuing to reduce pollution can help make that shade cleaner too. I'm Dr. Mack, and this has been The Climate Translation. If you have a question about the climate you've been too afraid to ask, or if you have a differing opinion, I want to hear from you. I can use your viewpoints in future episodes. You can reach me at theclimatetranslation@gmail.com. I'll see you next time.